Hello, everyone. Welcome to the next talk in our tutorial, where we will be speaking about performance monitoring. So here, given a perception model that is integrated in a safety critical system, we want to learn to identify the complex situations that may cause a wrong prediction or a failure from its side. To give you a bit more details, let's look again at the example of autonomous driving or driving assistance systems, where we have a perception system, a model that is somewhere in the middle of the driving system. So let's say that we see now in the real world some unknown scenario, some anomaly, maybe a plane that just flies overhead over the highway, or an elephant, or a jet ski like here that we have not seen during training. And this is what our perception model sees. And if it's not a robust system, robust model, it will give us a wrong prediction. And this wrong prediction will be used by another downstream system, like the driving stack, where it uses this to have an idea of this free space around the vehicle, or whether there's an obstacle or not. And since our prediction was wrong, it can lead to a propagation of this wrong prediction downstream. And if it's a very significant error, it can lead to an accident. So our goal here, given these complex systems that we can encounter in the real world, is how to identify and eventually prevent the incorrect predictions that can cause such system failures. So again, when looking in the challenges of driving automation, so we can see, taking this example from this paper of Rahman et al., where they analyze the behavior of an object detector. So they try to predict the performance of an object detector at test time, based across different traffic conditions. So here on the y-axis, we have the mean average precision, the MAP score for object detection. And here on the x-axis, we have the temporal dimension, where we analyze over a video sequence. We analyze the performance at each frame of our object detection model. So you can see here in green we have relatively high MAP predictions, but while we are here in a relatively easy scenario of on the highway on daytime, so we can see here in green that our perception systems estimates that we have a good performance in these conditions. Going then on the green light green curve. So this we can see that in here we can see that the performance is quite lower compared to the green one. So here we are in the city environment, which is depicted here during the day. So again, the performance fluctuates in time depending on the number of agents in the traffic, on the conditions, and also of the quality of our object detection model. And finally, we get here on the red curve, which is mostly the worst, rather the worst most of the time. And this is city by night. Again, even more difficult conditions compared to the original ones that we have on the highway, and the performance is in the 30 MAP score, MAP, or 20, or sometimes below, as in this part of the image, so of the plot. Sorry. So this performance can fluctuate depending on the conditions, and often in practice we have some strategies to look at the confidence of the object detectors, or if there's a semantic segmentation, or if the probability is given by an image classifier. So we have some systems that are engineered to monitor these predictions, their behavior, and they have essentially some thresholds to figure out whether there's an anomaly, there's a failure, and to decide whether this decision is reliable or not. However, given that we see more and more neural networks entering gradually in these systems, and most of the modules are starting now, many of these modules are starting to be replaced by neural networks, we may need to revisit also some of these monitoring strategies, and look also on more sophisticated mechanisms to figure out when our models are making a wrong prediction. Whatever the source of uncertainty it may be, often we might be interested when we are dealing with real-time systems, of whether we can put confidence or not into this prediction or not. So we're rather looking at the confidence, whether our model is going to fail or not. So we are looking for a strategy to figure out this, given the complexity of the real world, but also the sophistication of the neural models that we are gradually inserting in our system. So enter neural monitoring approaches. So we talked about the engineered ones. We asked the question, what if we can have a network that will learn to monitor another network? So here, the network that will be monitored, we called it target network. So this is our network that is trained to solve a task of interest, let's say here image classification, which makes some certain predictions. We use here to monitor, we define another network, which we called observer network, which is an auxiliary network taking the same input, but not necessarily taking the hidden activations of the target network. It doesn't necessarily need to take them all, but it needs to analyze to some extent some of the activations coming from this target network, and also looks at its output. So by analyzing the input and the behavior of this target network, our observer network is trained to predict the failures of this target network. So it often amounts to predicting a confidence score or a failure score or an anomaly score, depending on how we frame this problem for monitoring the behavior of this target network. So we can train it, as I said, to predict the confidence given by the target network. So this training of the observer network happens in the second stage, after we have pre-trained our target network for solving the task of interest. So, well, the training is rather straightforward. So if we have a correct prediction, we can train it to give a low anomaly score or a high confidence if we think in terms of confidence. Conversely, if we have a wrong prediction, so for example, here we have a fish and the prediction of our target network is a cat, we should predict a high anomaly score or a low confidence, because our model has given an incorrect prediction. The benefits of these types of methods are obvious because they are quite generic. They can suit to any type of architecture. They're also flexible, so they can take an arbitrary number of hidden features from the target network, but they do not necessarily need to have the same architecture of this target network. Sometimes they can be just a few layers at the end of the network, or depending on the resources that they can have, they can replicate exactly the architecture of the target network. They're usually fast, as I said, because we can modulate based on the computational resources and constraints that we have, the size and the behavior then the architecture of this observer network, and they're usually memory efficient, more or less in the same spirit that I've described before. The drawbacks, there's quite a few as well, unfortunately. So we need, and the major one is we need a dedicated training set to train the target network, and another one for training the observer network, because neural networks nowadays become very confident and have high performance on their training data set. So if we train our observer network on the same data set, we may not see too many errors. So we need a dedicated training set to have some samples that were not seen by our target network, such that we can have an idea on how this target network will behave on unseen conditions. Another potential drawback of these methods is that they may not generalize to OOD data that is not available at runtime. So they are usually trained to predict the confidence of the target network on a certain training data set, usually from the similar distribution as the target network, because we're usually limited in the amount of data that we can use for training. So as I said, coming back to this, the major challenge with these types of methods is related to the availability of hard training data. So this is often a chicken and egg problem, or a very difficult problem to look at, because if we have some hard training data, what do we do with it? Do we use it for training a very good target network that has seen quite a few edge cases and will be robust to different conditions at runtime? Do we use it for training our observer network such that it will be figuring out how is the model behaving on these really hard samples. So it will be more reliable at train time to figure out the anomalies and the errors that the target network has. Or do we keep it for evaluation to have on the side an actual performance assessment of the performance of our model in a real world condition? So this is a very difficult problem because this hard training data regarding corner cases and another difficult conditions is on the long tail. So we don't have much of it, or if we have of it, it's covering well, some long tail classes. But the problem with long tail is that there's many long tail items. So we are always put in a difficulty when dealing with these observer models, observer networks, on how to train them. So some people looked at different conditions where we train our observer network for, in particular in this case, for object detection. We train it in time, so we use the temporal information, and we train it to predict the the mean average precision of an object detector in this case. And we do not necessarily need to have all the annotations, or we have just some coarse boxes. So with time, we can actually slide through and analyze more context and get some additional information to train this observer network. So in this case, in this paper by Berahman et al., they follow the same principle. They have a target network which is frozen in the second stage, where we train just the monitoring system or the observer, which in this case is actually a small ensemble of boosted networks, and they are trained to evaluate in time and to look at the predictions from each previous time step to predict at the end of the temporal window the total MAP in that window. And then at test time, we have our target network that makes some predictions, and we have our observer network that will be predicting the mean average precision for over a given time window. So this is a very interesting approach, and it's actually quite effective. On the downside, it does not allow to have very precise predictions, because it just does boxes, so it cannot necessarily work for semantic segmentation. And it does not fully solve the problem of finding some harder training data on well, some secondary data sets for training the observer network. So in their case, they looked at time, which gives us the model a different dimension to explore, but we're still bound to the size of the secondary data set, and we may have the same dilemma on how much this secondary data set will be used for the primary data set to train the bigger the target model. So in the following, I'll propose another strategy for looking at for finding this training data for the observer network. So the starting point here is that we look at in different in practice, whenever we want to deploy a model in practice, be it a robot or a vehicle, we pass it through several stress tests. So here is an example from Boston Dynamics, where they look at the equilibrium and the capacity to recover of a robot by stressing it in different by pushing it back and forth to see how it will recover, or how it deals with these complicated cases. Another example here, which is a bit lighter, is with these robots playing football, and the researcher here tries to pull them and to push them back and forth such that they will recover, and put them to fail, and they eventually can recover, because they might have seen this type of conditions during training. So we built here an idea based on that, on asking, what if we find a way to make the this target model fail, and can we learn from that? So here the authors look at take inspiration from the adversarial attacks by Segit et al., where Segit et al. Showed that neural networks can be fooled by perturbing the input image just with some constructed noise, and such that when you applied it to the image, it will completely flip the class from, in this example, from panda to gibbon. So here we will use adversarial attacks to trigger some failures in the target network. So as I remind, the goal here is to find some sources of hard data without knowing that in general this real hard data is very limited. So in the case of semantic segmentation, in the paper by Bain et al., OPSNet, the authors propose to use local adversarial attacks, where given a training image in the a prediction that the target network gives, we apply an adversarial attack, but with the specific of being local. So here we apply an adversarial attack with a random shape. So we encrust it here in the image, and since we know that it's an adversarial attack, all these pixels here would be considered as having an error in them. So in this case, we essentially use these local adversarial attacks to hallucinate new classes. In this way, we know for sure that the model is failing there. So our observer network will now see how is the target network failing in some blind spots that it has. So the idea is not to be necessarily invariant to adversarial attacks, but rather to see different failure modes of our target network, such that at runtime, when it will see fishy behavior or something that resembles with an uncertain behavior in the feature maps and in the output, we will be able to recognize this with this observer network. And it's often, as I said, since we're dealing with autonomous driving perception and semantic segmentation, these failures should be related to an object. So this is why we have here a local adversarial attack, because we want to mimic some sort of object that we have not seen. So this is why our attack has a random shape, because we want to detect any unknown object that might appear at test time that we haven't encountered in the training set. So to illustrate a bit the training setup that we have in OPSNet, so again, we have our target network, which is a network for segmentation, and our observer network, which takes the input as input the same image, but also the hidden activations of the segmentation network. The segmentation network, as the name says, will predict a segmentation, while the observer network will predict a confidence map for every pixel in the semantic segmentation. So in a first stage, we train the segmentation network to do the segmentation, and then in the second stage, we apply adversarial attacks to the input image, such that the segmentation network will be fooled, and this gives us a segmentation map or supervision to align the uncertainty predicted by the observer network with the errors that will be at the output of the segmentation network. So so this is the behavior at train time. At runtime, the pipeline is more simplified. We just have I think I forgot to mention. So here the segmentation network is frozen. We don't touch it. We will backprop just through the observer network by looking at the ground truth predictions and the confidence that they have, and in the ground truth attacks that we have applied on a certain region of the image. So coming back to the runtime, so here we have an input image at runtime. We pass it through the semantic segmentation network and the observer network at the same time. The observer also takes with skip connections can take also the features from the target network. It's essentially plugged into it. As I said, we don't need to necessarily to have the same architecture. It can be just a few layers at the end, that are branched to the features of the segmentation network, and our model now predicts the segmentation. That also has a confidence, but we also predict the confidence from the observer network, and this is what we will be feeding to the downstream system to tell it whether it can rely on the prediction from our segmentation network or not, and if it can, at which areas of the image the predictions are reliable. So when we analyze the performance of OPSNet, so in this case, we looked at two data sets for out of distribution detection, BDD anomaly, which is a subset of the BDD data set, where in the train set we have removed from the train set we have removed the classes train and motorcycle, but we see them coming back at test time, and we are looking at the performance when predicting on these classes. And since we are dealing with failure predictions, we don't look just at OOD. We also look at the predictions that are incorrect on the in distribution classes. And we have a similar data set, which is synthetic, however, called street hazards, where we have all sorts of weird objects that appear at test time. So here we have a giant phone The idea is really to have some unseen and very unusual shapes that appear at test time, and to see how is the network generalizing to such out of distribution samples. So in this paper, there were numerous experiments on several baselines, ranging from the very simple ones such as softmax or void, where you have just a class for unknown in addition to the known classes. A reconstruction-based method, using temperature scaling for calibration. These are this is a method for auto distribution detection called ODNID, ConfidNet. So here we have a few ensembles that we've discussed before, in particular deep ensembles and MC dropout. And finally, there's the OpsNet with the local adversarial attacks. So what we notice is that while softmax, this is the baseline, that softmax, where you just use the maximum class prediction from the classifier. So we'll use this probability as a confidence score. So it's getting a decent performance. But whenever we look at deep ensembles and MNC dropouts, so their performance is improving upon this baseline, but it comes at the cost of multiple forwards. In the case of in both of the methods, and in the case of deep ensemble, we also have multiple networks, not just multiple forwards. So when we go to OpsNet and local adversarial attacks, we can see that for BDD, in some cases we reach the same performance or better than deep ensembles, in particular on FPR 95 TPR, in area under the precision recall curve, or the area under the receiver operating curve. And here, even in calibration, we are better than deep ensembles, and we see a similar behavior also in the synthetic data, where we have quite a gap compared to deep ensembles. So in terms of failure and the precision and also out of distribution detection, these types of methods that are specialized for detecting the failure can outperform deep ensemble, that are more expensive, but that could potentially have the advantages of diversity and of looking at different types of uncertainty, but they come at a bigger computational cost. And if we're interested just in failure prediction and some OOD there, we might be better off with something in the spirit of OpsNet. So I said before that we apply random shape attacks. So we looked at different types of applying the attack to figure out what things works best and why. So we initially looked at applying attack randomly on all pixels, and we see here the performance in terms of FPR 95 TPR. We applied square patches attack, so we just take a random square and use it as a mask for applying the adversarial attack. So here we see an improvement compared to applying to all pixels. Then we looked at applying the attack using the segmentation masks and perturbing a certain class. So in this case, we perturb just the cars, and we can see that actually this is a bit worse than the square. So on this metric, the lower the better. Well, when we apply a random shape, we can see that our performance is quite a bit better compared to the other baselines. And we argue is that, as I said before, since we're looking at a random shape, we may generalize to very weird or unknown object patterns that we have not seen during training. When we apply it here in the shape of the car, well, the model has already seen cars, and there might be a confusion between, it might be thinking that OOD objects may have the shape of the car. Here, the square is actually a bit better than the car, because it remains an unusual shape, but our classifier may overfit to this square shape. While here, when we are applying a random shape, so essentially we conflate different circles, ellipsoids, and we overlap them, and we take the outer area of this overlap. We have some very unusual patterns that we argue help our model discover more blind spots. Our observer network see more blind spots, a diversity of blind spots in the target network to better recognize them at that rate time. So when we look at some qualitative results, here is a toy data set where we've split some animals on Canvid. So here we have a giraffe, and here we have a tiger. This is the segmentation that our model produces. This is the obstinate uncertainty prediction. This is a softmax and the MC dropout. So we can see that all models fire on the borders of the frontiers of the object. So this is normal with the entropy, and also with the softmax. But what we can see in addition to that is that our model fires quite a bit more with higher uncertainty on the unknown objects that it has seen. So since our method is also predicting the failures, so it does not look just at these unknown objects, we can have uncertainty also here in these areas for which our ground truth might be more fuzzy. So it could be an instance of the aleatoric uncertainty that we have mentioned just a few talks ago. When we look at BDD anomaly, which is a data set from the US, I remind here that we have as anomalous objects the motorbikes and the trains. Here I'm showing some examples with motorbikes, the segmentation, and here we have the results of OpsNet, and we can see that the unknown objects are clearly highlighted here with higher uncertainty compared to the softmax, also compared to the dropout, which also gets them relatively right, but not with the same uncertainty, and while requiring several forwards, which come with a higher computational cost. So when we analyze the precision versus time computational trade-off, here we show the OROC and here the flops. We can see that MC dropout, and this is an ensemble technique called Gaussian perturbation. They require more flops because of the different number, several forward passes. Here we look at deep ensemble, which has here we use the smaller ensemble of 3 networks. So it has a higher cost, but it's still decent. And we compare with our OpsNet plus local adversarial attacks. We can see here that OpsNet is computationally lighter and has a higher performance on this auto distribution detection compared to deep ensembles. And we have here a few other baselines from the mean classifier, maximum classifier prediction, which is the softmax, and ODIN, which is for out of distribution detection. And we are outperforming all while being computationally appealing. So we can see as takeaways that while we can do a decent job with observer networks with local adversarial attack story to find the blind spots in the target network without needing to mine for even more real hard negative data. So we focus here on localized regions to mimic unknown objects. And with the way we have these local adversarial attacks, we can potentially generate infinitive negative examples to find many other blind spots of our model, of our multi-million parameter model. And there's certainly different blind spots that we can find with adversarial attacks. So this idea of using a confidence estimator network observer network has been subsequently applied also for regression, which is good news that these type of methods can also be as generic as ensembles, as they can be tuned for different types of architectures and tasks. On the downside, however, since it's a segmentation, we cannot actually localize precisely the object that is anomalous. So here we have highlighted it by hand in red, this object. But from the segmentation map, it's not that easy to figure out that this is an object, and all these other errors might be related to different sources of errors. So this is something that is currently addressed in some ongoing works that appeared, recent works that appeared on Archive or that are currently in progress. And another drawback of this type of methods is that the predicted error is quite generic. So as I said just before, it's not easy to map a high error to a specific type of uncertainty. So here visually we can assess that it might be an instance of aleatoric uncertainty because it's farther away pixels. Here we have a reflection on the windshield, and again it might be some aleatoric uncertainty because it hinders the visibility. But then for the others we don't know. So this is an epistemic uncertainty because we have an unknown object. But figuring it out just from the value, it's not trivial, and it's subject for future work to be improved on. So with this, I will conclude. I'm concluding the performance monitoring section, And I'm looking forward to see you in the next talk, where we'll wrap around the findings on this tutorial, and we'll provide some trends and perspectives for this area, for people that are currently working on it, or that are currently looking for ways of integrating these ideas in their own work. See you in the next video. Bye-bye.